Hey guys, so today we're going to be looking at exponential functions, and we're going to be looking at what each variable does to our exponential function. And when I say an exponential function, I'm talking about the standard form of y equals some constant a times some constant b raised to the x power plus c. Each one of these variables is going to dictate important information about the graph. And what we realize is if we graph this and visualize this with sliders on Desmos, we can actually generalize what each variable does to the formula. Let me show you what I mean. So if I go ahead and I type in y equals a times b to the power of x plus c, we're going to be able to create some sliders here to go ahead and check out what happens when I have an exponential function. Now remember, an exponential function is any function that increases constantly as we go. So if you looked at the slope of this function at any given point, at this point we could find the slope of the function by taking a simple derivative. You'll learn how to do that in calculus. But if you picture laying a flat piece of wood across this point, you could see the slope of the line would look something like this, right? And if I go up here to a different point, let's say we go right here, we can see the slope of this line is going to be much steeper. And if I continue to zoom out, I can see that the farther and farther I go up, it's going to be even steeper. What I notice here is right away, when I entered in all my sliders, when all my values are 1, this line is a straight line. It's not an exponential function. You know, if I change a, it's still not an exponential function. If I change b, it's still... If I change c, it's still not an exponential function. But if I change b, it is an exponential function. So the very first rule we're going to learn is if b is 1, it's not an exponential function. So b cannot be 1. And I notice if b is greater than 1, the exponential function is increasing as x goes on. And if b is less than 1, the exponential function is decreasing. But once I get to 0, notice I do not have a function in the negative values. So right away we see that b has to be greater than 0, and it cannot get perfectly at 1, otherwise it's no longer an exponential function. So between 0 and 1, this function is decreasing as I go on. But if it's greater than 1, we see our function is always increasing. So that's our first distinction. So let's go ahead and let's leave this at, let's say it's at 2. Okay, so I also notice that when I change c and a, they're very predictable changes. Okay, so c is probably the most predictable. It's a very simple correlation here. If I put c up to 5, what do we notice about my graph? Let's move it up to 5. Do you notice where c being equal to 5 affects this graph? What about if c is 4? Do you notice where 4 comes into play in this graph? What about if c is 3? Do we notice where it comes into play in this graph? And hopefully you're picking up on the fact that if c is 5, I notice that what's called my horizontal asymptote, meaning the line that this function levels off at and never crosses, it's at 5, the same as c. And if I put c down to 4 exactly, I notice that this function goes on and on and on, but never crosses and passes 4. No matter how much I zoom out, this function is going to get close to 4, but it's never going to pass it. So c is going to dictate what we call the horizontal asymptote. So that's going to be really helpful. And lastly, a, while we might not be able to predict what a is at the moment, we do know that when a is positive, where is my graph going? And when a is negative, where is my graph going? It looks like when a is positive, the graph is staying above the horizontal asymptote, and when a is negative, it's staying below the horizontal asymptote, right? If I change this it stays below it. And even if I go ahead and I make b 0.7 so that it's approaching the horizontal asymptote as x gets bigger. But a still is below the horizontal asymptote when my numbers are negative. It's not until I make a positive that my values are above the horizontal asymptote. So this is a lot of information. I would like to go into the why in a future video. For right now, let's summarize what we've just discovered. So in my standard equation, y equals a times b to the x power plus c, we learned that a, b, and c dictate specific things. C is probably the easiest. C tells me where the horizontal asymptote is. Okay. B, we determined, had a very specific set of rules. We knew that b had to be greater than 0. So I'm going to just go ahead and put it this way. B is greater than 0, but it also couldn't be equal to 1. And we found when b was between 0 and 1, and when b is between 0 and 1, we would say that b approaches our horizontal asymptote. And then when b was greater than 1, we said that it goes further from the asymptote. This is kind of slang terminology, but basically what we're trying to say is that if I have b being greater than 1, wherever my horizontal asymptote is, as I go to the right on the graph is going to get further from that asymptote. And if b is less than 1 but greater than 0, as I go to the right of the graph, it's going to get closer to the horizontal asymptote. And then lastly, a was pretty simple. If a was positive, meaning if it was greater than 0, then the graph lied above the horizontal asymptote. And if a was negative, meaning it's less than 0, it was below the asymptote. So this is a lot of information here, but it's going to be helpful when we're sorting things out. And let's go ahead and let's do a couple examples to see if you're getting the hang of this. So here we have a function. I don't know what the equation is. The question I want to answer is which of these functions best describes this graph? Well, based on what we know that as this function goes to the right, my function approaches my horizontal asymptote. So since it approaches the horizontal asymptote, we should probably expect that b is going to be somewhere between 1 and 0. So in this situation, b is between 1 and 0 in both of them. We also see that the horizontal asymptote is at y is equal to 3. So that means that my horizontal asymptote should be c is equal to 3. So that looks good in both equations, but a is different in both equations. So which one of the a's is it going to be? Positive 3 or negative 3? Well, when I look at this, my distinction here is if a is positive, it lies above the asymptote, and if a is negative, below 0, it lies below the asymptote. And we see here that a lies below the asymptote, so I should expect a to be negative or less than 0. And the one that satisfies that is this one. So it cannot be this first equation because the 3 should be negative if I have a negative number there. And so this is going to be the right equation. Now, do I know that these numbers, negative 3 and 1/2, are going to be the exact numbers? No, I don't. But this is the best answer. It's better than the first one because this 3 needs to be negative, not positive, because of the rules that I said before. Let's go ahead and let's watch one more example. All right, so we just went ahead and erased all of our work just to redraw some more. And I went ahead and I gave you 3 equations here. So in this example that I've given you of the graph, the blue function, which of these 3 equations best describes the blue function? So let's go ahead and let's observe a few things about our blue function over here. What do I notice? I'm going to draw little glasses here just so I can say what I notice about this function. I notice that it goes away from the asymptote. So it's further from the asymptote as x goes to a positive infinity. So as I go this direction, my graph goes further and further away from the asymptote. So that's number one. And that's probably going to tell me, since this is when it's further from my asymptote, that b is going to be greater than 1. Just keep that in mind. So b is greater than 1. I also notice that my graph is above the asymptote. It's above the asymptote. What that means is, that tells me what a is. If my function is above the asymptote, then that means that a is greater than 0. So a has to be positive. And again, remember, we're always referring back to this standard equation. A is greater than 0, a is positive. And then lastly, my horizontal asymptote. I do not know what exactly my horizontal asymptote is, but there is one point of information that I know about it. It's above the x-axis, so that means it's going to be positive. So my horizontal asymptote is positive. It's greater than 0, which means my c also has to be greater than 0. Because if my horizontal asymptote is 1, for example, then that means c is 1. If my horizontal asymptote is -2, then c is -2. So since my horizontal asymptote is positive, not knowing what number it is, then I also know that c is positive. I don't know what number it is, but I know that it's positive. So keep these three important pieces of information in mind. And let's go ahead and let's look at number 1. So number 1, my a, remember my function is y equals a times b to the x power plus c. So my a in this example has to be positive because my function is above the asymptote, so that's good. My b has to be greater than 1 because it grows away from the asymptote. That's good. And my c has to be positive. So this is good. So for all purposes, number 1 could work. So I'm going to go ahead and I'm going to circle number 1 right now. This could work as an equation. Do I know this is the exact equation? No, but it could work. On the other hand, let's look at number 2. Right away with number 2, a needs to be positive. Is a, my a term, positive? Yes, it is. B needs to be greater than 1. Is b greater than 1? No, it's not. And even though c is greater than 0, it doesn't matter. This isn't possible because if number 2 was drawn out, since b is less than 1 but greater than 0, that means that it would approach the asymptote as it goes to x, which means this graph would look something like this, which is not the graph that we've been given. So 2 cannot be an answer. Let's look at 3 though. Let's see this one. Is a greater than 0? Yes, so that's good. Is b greater than 1? Yes, that's good. Is c greater than 0? Yes, it is. So this also could be an equation of the graph. So not always will you get examples where more than one answer could be possible. Usually you'll get 3 or 4 solutions and only one of them actually could work. In this example, I just wanted to show you it doesn't matter what the numbers are. What matters is b greater than 1, is a greater than 0, and is c greater than 0. So when you're working on this, keep these details in mind, keep what we learned in mind about our graph on Desmos, and then this is going to be something that you can do.